Today we're going to be talking about rates of change and the derivative. So first example, consider a door with an automatic closer. At t equals 0 seconds, someone pushes the door open. It swings open, slows down, stops, then starts closing. It closes slowly until it hits a certain point. When t equals 7, it slams shut. As the door is in motion, the number of degrees, d, it is from its closed position depends on time. And first we're going to schedule a reasonable graph. So on our x-axis we have time, and on our y-axis we have the number of degrees it's open. So this whole thing starts at 0 and ends at 7. So the door opens, so the degrees are going to get bigger and bigger and bigger and bigger. Then it stops being open, which means the degrees are going to get closer and closer and closer, and then it's going to slam shut. For part B, suppose that it's defined by this function. So d of t is 200t times 2 to the negative t. We're going to plot this in the calculator and sketch the results. So in the y equals, we're going to go ahead and type in our function. We'll type it in, but we're going to use x instead of t, and then we're going to graph it. So we don't really know what the range of this graph is, but we do know the domain. So I'm going to use the table to figure out what my window should look like. So if I go to second table set, I'm going to start at 0, and I'm just going to go up by ones. Then I go to the table, and I'm looking at the numbers from 0 to 7. Okay, so this goes from 0 to 100, 100, and then back down. So I'm going to make my window maybe a little bit bigger than 100. So I'll go from 0 to 7 in the x values, and then the y values, I'm going to go from 0 to maybe like 120 or something like that. So here's our graph. We're at 0, 1. Our maximum is somewhere in between 1 and 2 there. So maximum is about 1.5. So we'll copy this graph down in the notes. So we graphed from 0 to 7, and in the x directions, 0, 120 for the y range, and the graph approximately looks like this. So at time t equals 1, does the door appear to be opening or closing? So t equals 1 is here, and the graph is going up, which means the number of degrees is increasing, which means it's going to be opening, because the graph is increasing, meaning the number of degrees is going up. Time equals 3, we're on the decreasing side of the graph. So we're going to say it's closing because the degrees are decreasing. And then it says, is there a time when the door is neither opening or closing? And that's going to occur at the maximum. So yes, at the maximum. Next, we're going to find an estimate for the instantaneous rate at which the door is moving at time equals 1. So at time equals 1, we want to figure out how fast at that instant moment is the door opening up. So what we're going to do is test points very close to 1. So 1 to 1.1, 0.9 to 1, 0.9 to 1.1. So this first one is a right-hand estimate because we're doing the value we want and a value a little bit bigger. So we're going to look at the slope because that's the rate at which it's changing. So we're going to look at d of 1.1 minus d of 1 over 1.1 minus 1. Now we're going to let the calculator do the work for us. So on the calculator, I'm going to show you a neat trick. Okay, so I have my function that I'm interested in stored in y1. So what I'm going to do, I'm going to do alpha f1 to give me the fraction. And if you don't have the fraction, that's okay. You'll use parentheses. Then I'm going to use my y values. So I'm going to evaluate the function y1 at 1.1 and at 1. So if you go to alpha f4, you're going to see y1. So I'm going to select y1, and I'm going to plug in 1.1, close parentheses. So this is evaluating my function at 1.1. I'm going to repeat that, so alpha f4 y1. And then I'm at 1.1 minus 1. Then I'm going to hit enter, and I get 26.336. So at that instantaneous point, it's opening at about 26 degrees per second. So first thing, in calculus, in AP, the standard is 3 decimal places for everything. No significant figures, nothing like that. 3 decimal places, and you can either round it or truncate it. Okay, the units here, the units on the top, because this is the function, is degrees. The units on the bottom are the seconds. So that's what that degrees per second. We're going to repeat that for these two. So for this one, I'm going to do d of 1 minus d of 0.9 over 1 minus 0.9. This is a left-hand one. So again, we're going to use the calculator. So I'm going to grab that and change this to 1 and 0.9 and 1 minus 0.9, and we get about 35. So that's 35.404 degrees per second. So that one was 35, and then this last one, same exact thing, just the different numbers. We get 30.8. So we've got a 26, a 35, and a 30. So those are 3 approximations for what's happening at 1. So based on your answer, does the door seem to be opening or closing? Again, opening. And this time it's going to be opening because those are positive values. The rate of change is positive. So just quickly, to estimate at 3, I just did a symmetric. You can pick. So I did 3.1 and 2.9. We got negative 26, which means that it is closing at that time. And then explain how we could get the average to estimate the instantaneous. We're going to use limits, and we're looking at the limit as the distance between the two numbers approaches 0. Here's our next example, so go ahead and pause it and read through that. So our dinky is going from Princeton University to Princeton Junction, which is 2.7 miles away, and this graph shows the distance where it is relative to Princeton University. So when is the dinky headed toward Princeton University? Well, that means it's going to be here moving this direction. So that's going to happen between 7 and 10 seconds. At 10 seconds, there's this little pause. So he's not moving any closer. But then at 11, we start moving again all the way to 13. When is it headed towards the junction? That's going to be from 0 to 4. When is the dinky stopped? That's going to occur when the graph is horizontal. That means it's not moving any closer or farther away. So that's going to be from 4 to 7, and from 10 to 11. The average velocity from Princeton to Princeton Johnson. So from here to here, the average velocity is going to be the distance over the time. So the distance traveled is 2.7, and how long did it take him to get to the 2.7? 4. So that's approximately 0.6 2.75, and this would be miles per minute. The average velocity for the whole trip is going to be the total distance traveled over the total time. So the total distance is 2.7 this way and 2.7 this way. So I'll just do 2.7 times 2. And the time it took to do that is 13 seconds. So this gets us about 0.415, again, miles per minute. So we have a tire is punctured by a nail. As the air leaks out, the distance y between the rim and the pavement depends on time t minutes since the tire was punctured. And here's our chart. So approximately how fast is y changing at t equals 2 minutes? Okay, so again, this is a rate of change. So we're going to use the values in the table. I can't do it exactly here. So what I'm going to do is I'm going to pick the times surrounding 2. So I'm going to do 4.42 minus 6 over 4 minus 0. So it's just this point minus this point is going to give me my rate of change. So this gives me about negative 0.395. The units here are inches. The units here are minutes. So negative 3.95 inches per minute. We repeat that process for t equals 8. So I used 6 and 10 and those two values. Plugged it in and got negative 0.14. So how do you interpret the sign at which the rate is changing? So this is a negative. Okay, that means that the distance between the rim and the ground is decreasing. These numbers are getting lower and lower and lower, so that tire is getting closer and closer to the ground. This next problem, the graph shows the temperature, T of x in Celsius, of the kettle of water at time x in seconds since the burner was turned on. So the temperature is here, the burner gets turned on, so the temperature rises, then it levels off here, and then it starts to decrease. So we're asked to draw the tangent lines at x equals 40, 100, and 140, and we're going to use the lines to approximate the instantaneous rate of change of the temperatures at this time. So at 40, so when we draw a tangent line, we're just trying to match the slope at that point. Okay, and then we'll do one at 100, or not 100, at, 100. So tangent line there's gonna look like this. And then my last one at 140. So we're just trying to match that slope. And these are just approximations. So when x equals 40, we're looking at this slope. So you're looking, and it's a little bit tough to see, but we're going from about 60 up to, 60 to 90. So that would be a change of 30 over a change of, these are going up by 20s. So 30 over 20, so maybe approximately 1.5 degrees Celsius per second. This one's changed. That slope is pretty easy to determine. That slope is going to be 0 degrees Celsius per second. And the last one slope, looking here, it's going down, maybe about going down negative 20 over maybe 15. And these are just estimates, so you're just doing your best guess here. So negative 15 over 10, which is about those are 20, sorry, that should be 20. Negative 0.75 degrees Celsius per second. Then we have, what do you suppose is happening for the between 0 and 80? So the temperature is rising, so it's heating up. Okay, at 100, it doesn't change, and you know from experience, that means the temperature is not changing, which means it's boiling. It can't get any hotter than boiling. It just stays there. And then from x is greater than 120, it is cooling. So there's a definition here, and we've kind of been doing this. The average velocity is going to be the change in distance over the change in time. So distance over time. So how far have you gone and how long did it take you? That's average velocity. If I want the instantaneous velocity, we're looking at the limit as that change in time goes to 0. So it's going to be the limit as the time approaches our time that we are interested in. So we're looking at a single location. So let's work with that. So the equation for free fall at the distance of Mars is s of t 1.86 t meters, and we're going from a 200 meter cliff. So how long does it take for the ball to hit the ground? So we're going to look at how long does it take 1.86 t squared to go a distance of 200. So if I divide 200 by 1.86 and then take the square root, we get a time of about 10.370 seconds. Okay, what is the average velocity during the fall? So average velocity is the distance, the change in distance over the change in time. Well, when a distance of 200 meters, and it took us 10.370 seconds to make that happen. So my average is 7.44 meters per second. If we want the average for a smaller window, so this is the average over the entire fall. If I want to look at a more specific range of values. So I want the change from 1 to 3. And I just now realized I was looking at my notes wrong. This number should be 19. Oh my goodness. Okay, this should be 19.287 meters per second. Okay, this one, so the position at 3 minus the position at 1 over 3 minus 1, that gets us 7.44 meters per second. We take that idea, now we want to look at the velocity at t equals 1. Well, I can't plug it in. We want the instantaneous velocity. So that's going to go back to our limit definition. So we want the limit as t goes to 1 of s of t minus s of 1 over t minus 1. So looking at this, I want this other point. So here we looked from 1 to 3. I want to get as close to that point of 1 as I can. So s of t is, goes to 1. S of t is 1.86 t squared. S of 1 is 1.86 times 1 squared over t minus 1. I'm going to factor here. So I'm going to factor out the 1.86, which leaves me with t squared minus 1. Then I have the difference of two squares. So this is going to be the limit as t goes to 1 of 1.86 t minus 1 t plus 1. Okay, the t minus 1's cancel. We'll plug 1 into what is left, and you're going to get 3.72. This is going to be meters per second. Okay, for equation of a tangent line, we're going to use point slope form of a line. We're going to use that a lot in here. Okay, so we just need a point and a slope. So at time 1, my position is 1.6. So I'm going to have 1 minus 1.86. My slope is the 3.72. That's the rate of change. Times x minus 1. Okay, this is going to be the same thing we did here, just with 3. So you guys can do that on your own or look in the notes. This one we're going to do the same thing just generically for t. So we're going to look at the limit as t goes to some time that we are interested in. So that's going to be f of t minus f of t that we're interested in over t minus t. We'll just call it naught. So we're going to factor this will be the difference of squares again. So we factor that, those cancel. That leaves me with the limit as t goes to t naught of 1.86 t plus t naught. Then I'll plug in this for the t. So this is going to be 1.86 t naught plus t naught. So that'll be 2 of those. So this is going to end up being 3.72 times whatever the time is. Okay, so now we're going to look at the slope of a curve. So if I want the slope at a point, we need to use a secant line to approximate this. So this is going to be a point that I am interested in. Okay, so this is A, this would be f of A. Okay, so what I'm going to do is I'm going to pick another point on this. And I'm going to say this distance here is h. So this is going to be A plus whatever that h is, that distance h. Okay, so this point is going to be f of A plus h. Okay, so that would be the slope of this line. And what I want to do is make it so that h is 0. Okay, so we're going to use limits to do that. So that's going to make, so this is, here's some notation. This is going to be the derivative. This is going to be the slope at point A. So the slope, and this symbol here means derivative, is going to be the limit as h goes to 0, so as that h value gets a lot smaller and smaller and smaller, of the slope of the secant line. So the slope of the secant line is going to be f of A plus h minus f of A over the difference in the x's, which is going to be A plus h minus A. Well, this is going to simplify to f of A plus h minus f of A all over h. So this gives me the derivative, the slope, at any point on a curve. Okay, so the derivative. Okay, the derivative, the geometric representation is that it represents the slope. So it's the slope of the tangent line to f of x at A, or when x equals A. So at that value, that is the slope of the tangent line. It is the slope of the line at A. The rate of change function interpretation of the derivative is that f prime of A is the instantaneous rate of change. So anytime you see the words find the instantaneous rate of change, we're going to be using a derivative. And then the physical representation, and this is going to, for those of you in physics, this will kind of make sense. If S of t is the position, then S prime of t, the derivative of t, is the velocity. So in different situations, if we take the derivative of position, we get velocity. Okay, now I want to find the slope of this at this point. So we're going to be using this definition. We're going to be finding the derivative of the parabola using this formula. So we're using the limit as h goes to 0 of f of a plus h minus f of a over h. My a is the point I am interested in. So this is going to be f of 2 plus h minus f of 2 over h. So for this part, I'm going to plug that into this formula. So this is going to be 2 plus h squared minus f of 2, which is 4. I'll FOIL. So we're going to have 4 plus 4h plus h squared minus 4. So the 4 minus 4 goes away, and I'm left with 4h plus h squared over h. So those will both reduce. To 4 plus h. So as h goes to 0, this is 4. So we're saying that the slope at point 24 is 4. For the equation of the tangent line, I'm again use the point slope form. So we're going to have y minus 4 equals my slope 4 times x minus 2. The equation of the normal line, that's a line that's perpendicular, is going to be y minus 4 equals, we'll do the opposite reciprocal, so negative 1/4 x minus 2. Okay, and then we're going to graph. So if I graph so my parabola, x squared, 2 is 4. There's y equals x squared. The tangent line is the line that has a slope of 4, and it's going from this point. So I'm just going to approximate it. Okay, and then the normal line is going to go perpendicular to that. So we're going to do one more derivative using our limit definition called a difference quotient. So the derivative of this function at x equals -1. So I am looking at the limit as h goes to 0 of f of a plus h minus f of a over h. So for this, we're looking at f of -1 plus h minus f of -1 over h. Okay, so here I'm going to plug that in. So we're going to have 2 times -1 plus h squared minus -1 plus h minus 7 minus f of -1. I plugged in -1 and got -4. Okay, so we've done these. So my next step, I'm going to expand everything out. So I'm going to FOIL this. So we're going to have 2 times 1 minus 2h plus h squared. That's this FOILed. Then I'm going to have plus 1 minus h, and then negative 7 minus a negative 4 gets me a negative 3. Then I'll distribute, so I'm going to have 2 minus 4h plus h squared plus 1 minus h minus 3 over h. I'm going to combine my like terms. So I'm going to have 2 plus 1, which is 3, minus 3, which is 0. I'm going to have a negative 4h minus h, so that's a negative 5h plus h squared. Divide out those h's. So we have negative 5 plus h. Then we plug in 0 to get negative 5. So that means the slope of that parabola when x equals negative 1 is negative 5. Thank you for watching.